Clustering is one of the most powerful techniques in machine learning when it comes to deal with unlabeled or unsupervised data. In this video, we will discuss k-means clustering algorithm in details, and in order to make it interesting and practical, I will not use any abstract datasets or the datasets which are of limited applications. Here, we will concentrate on using word embeddings and applying k-means clustering. So word embeddings are very important in the field of natural language processing. And in order to start with embeddings, we will first import the SentenceTransformer library, which is library containing large language models specialized for embeddings. Embeddings are the way to convert natural language into the multidimensional vectors. So we can convert a single word, a pair of words, or triplets of words, or entire sentence using large language models. As an output, we will update a numeric vector, which we can analyze later with various algorithms. So in this particular example, I will use 10 pairs of words, which are grant access, revoke access, access profile, add user, delete user, modify user, and create user. Finally, disk space, disk full, and disk error. So you can guess that these key phrases coming from some different classes of sentences, and they represent a particular messages of a certain class. So for example, grant access, revoke access, and access profile can be attributed to some sentences or messages or tickets which are related to the access. All the user-related pairs can be attributed to some user-related activities, again, like support tickets or administration rules and so on. And finally, disk space, disk full, and disk error can be attributed to some context which is related to their disk space, disk capacity, and so on. Indeed, these 10 pairs coming from the support ticket dataset, which is designed to show the end-to-end pipeline of how to deal with the natural language processing in the context of support tickets. However, in this video, we will only use with words. If you want to dive into all the details how these pairs of keywords were obtained, you can visit Support Ticket Classification Notebook, and also you can directly investigate Support Ticket Dataset. So once our SentenceTransformer model has been loaded, we will go ahead and apply this model to obtain embeddings for our pairs. For this, we will call the model, encode, and provide pairs as an argument. We can see that embeddings has the shape of 10 and 768. So 10 is a number of pairs which we have. So we can see that each pair has been converted into 768 dimensional vector. Usually 768 dimensional vector is a vector size for the embeddings of base BERT model. In contrast, there is a large BERT model which is using 1024 dimensional vectors for embeddings. However, in this case, the basis model for all MPNet base v2 is a base BERT-based model. Therefore, we have the output of 768 dimensional vector. Next, to make this data a little bit more understandable and more feasible for visual analysis, we will perform a dimensionality reduction. For this purpose, we will use principal component analysis from scikit-learn library, and we will boil down 768 dimensions into 2 dimensions only. This way, we will be able to visualize these embeddings in 2-dimensional space. So here we import principal component module from scikit-learn library and apply the transformation to embeddings of our pairs of words. Next, for the future exercise, we will define centroids, which will be used later. Now, we will visualize our points in 2-dimensional space, and here we can see how these points are distributed. So let's have a closer look what we can do with these points. We know that revoke access, grant access, and access profile, these keywords are derived from the context about the access. Modify user, delete user, add user, and create user are derived from the context of user management. And disk full, disk space, and disk error are derived from their hard drive or disk management context. In the semantic of language, these keywords seem very similar within the groups rather than across the groups. What I mean is that revoke access, grant access, and access profile are more similar in context of a natural language than other pairs. Furthermore, disk full, disk space, and disk error are also more similar to each other in the context. And finally, delete user, modify user, add user, and create user are more similar to each other than other keyword pairs. We can see that in two-dimensional space, the embeddings for each of the groups of these keywords are closer to each other within the group rather than the embeddings across the groups. So now we would like to come up with the algorithm which will allow us to do this grouping or clustering in an automatic way. And with a method we are going to apply is called k-means clustering. The idea behind the k-means clustering is as follows. We should define a number of clusters. We should define a number of clusters before the start an analysis. So in this case, we will assume that we should have 3 clusters, and each cluster will be characterized by 2 things. So first of all, each cluster will have a center. So we will have a centroid point. This is 2-dimensional point, which will be a center of the cluster, and we set it randomly. So we will have 3 centroids. These centroids are marked with red, green, and blue cross marks. So now, when we can see the location of the embeddings of the keywords inside the 2-dimensional space together with the centroids, we would like to assign these embeddings to particular clusters or group them. In order to do that, we should perform 2 steps. First step is a cluster assignment step. We'll assign embeddings to particular clusters by the following rule. We will compute a distance between a given embedding. For example, it will be delete user, green centroid, red centroid, and the blue centroid. So the Euclidean distance in this case is a measure of similarity. The closer embedding to the centroid, the more similar it is. And we will perform this operation of computing the distance between each embeddings and cluster centroids. Then we will select minimal distance. So for example, in this case, the minimal distance is between delete user embedding and the green centroid. And to doing this, we will assign indices to the centroids. And once we find out that a given embeddings has the minimal distance to a particular centroid, we will assign the index of that embedding to that cluster. Now let's go ahead and check the code. So the first step is a cluster assignment step. We will import SciPy library, which will allow us to compute Euclidean distance. We also have a detailed video about Euclidean distance computations and the meaning. You can find it in the description below. So now we'll create a loop for all the embeddings, and we will get the index of embedding. Inside the loop, we will go through the centroid values, which are stored in centroid dict variable. We will compute a Euclidean distance between each embedding and each centroid, and then we will compute a square root of Euclidean distance. Then we will find the minimum distance and get the index of the minimal distance. So in this way, we will understand which cluster we should assign given data point or given embedding. Let's have a look on the actual run of this code. So first, we will take a data point which corresponds to a ground axis. In 2-dimensional space, these embeddings look like this vector. We have 3 centroids. First is 0, 0.4. Second is minus 0.2, 0, and the third one is 0.4 and minus 0.1. The distance between these embeddings and all the centroids are as follows. And the minimal distance is 0.578. Therefore, this is cluster 0, and when we assign ground axis embedding the cluster 0. The same way we are doing for all the remaining 9 points. In total, we repeat this computation 10 times. This is cluster assignment step. Here you can see that of the first run, the revoke axis and ground axis, they are closer to red cluster rather than to all the others. The closest cluster for disk error, disk full, and disk space is blue cluster, and in the closest cluster for access profile, delete user, modify user, add user, and create user is green cluster. And as you can see that in this case, access profile, we would expect to be related to the red cluster. However, in this case, it belongs to green cluster. However, this is only the first step of the k-means clustering algorithm. Then, so the second step is Centroid update step. What happens here is once we assign data points to the cluster, now we will update the centroids themselves. In order to do that, we take an average across all the data points within given clusters, and we will assign that average to be a new centroid. So in this case, the centroid should move to a new location. So let's perform the centroid update step and see how centroids change after that. Here I also define some auxiliary variables. So centroid dict in time is a dictionary which will track the centroid dictionary variable, which contains the dictionary of centroids. So we have a key value of 0, 1, and 2, which corresponds to our cluster indexes. And for each cluster, we will have a value of a centroid, which is a two-dimensional vector. So this is how the centroid dictionary is organized. And then for each iteration or for each epoch, we will record the centroid step. On the other hand, we will have another variable called centroid in time. In this case, the keys of this dictionary will be indices of the clusters. However, as a value, we will have a list which is tracking different values of centroid for a certain cluster across the iterations of epochs. I will explain what iteration and epoch means in the following context. So let's run the code and we will see how our centroids will change. So the original value, the red centroid, was here, and now it's moved in the middle of revoke access and grant access embeddings. The original value of centroid 1, or the original value of green centroid, was here, and now it's moved somewhere inside the triangle between modify user, delete user, and add user. You can see that access profile is kind of already an outlier for the green cluster. And then finally, for the blue cluster, blue centroid moved from its original place inside the triangle of disk error, disk full, and disk space. So now the cluster assignment step and centroid update step together constitute a single epoch or iteration. So this is iterative algorithm. The more iterations we perform, the more stable the centroid values should become. So now let's run multiple epochs. For this purpose, we will update the code slightly. We'll take our cluster assignment step code and cluster update step code together. We'll wrap it in a for loop for the number of iterations or epochs. And also we will redefine the centroid dictionary with initial values of centroids, and we will redefine centroid in time, centroid dict in time, and clusters in time. For clusters in time dictionary, we will have a keys as iterations, and for each iteration, we will store the structure of the clusters. In other words, we will map an index of a cluster to the list of the data points which belong to this cluster. So let's run this code for 3 steps, and we will investigate the results. So now we have 3 iterations, and now let's inspect our cluster dictionary. You can see that cluster dictionary contains 3 keys, 0, 1, and 2. These are indices of our clusters. The 0 cluster contains entries 0, 1, and 2. The second cluster contains inputs 3, 4, 5, and 6. And the third cluster, which has index number 2, contains data points 7, 8, 9. Now, if we have a look at the centroid dict in time, we will see how the cluster centroids evolve in time. We begin with our initial values for the centroids. This is our -1, or iteration -1. After the first iteration, the centroid values are updated, and it's significantly different from the original values. Then for the second iteration, we can see that for the second cluster, centroid value almost doesn't change, but the values are changing for the first cluster with index 0 and second cluster with index 1. And finally, we can see that during the second iteration, none of centroid values has been changed. And that is an indication that our algorithm has converged. Now let's have a look at the centroid in time. It should have 3 keys. So this is our history of centroid for cluster 0. Centroid in time dictionary represents a history of updates of centroid values. So first we have our initial value. Then this is the value after the first iteration, this is the value after the second iteration, and this is the value after the third iteration. And similarly for cluster with index 1 and cluster index 2. Clusters in time dictionary contains the evolution of how data points were distributed across the clusters. For example, for the first iteration, cluster 0, which is our red cluster, contains 2 data points, 0 and 1. Cluster 1, which is our green cluster, contains 5 data points, 2, 3, 4, 5, and 6. And cluster 2, which is our blue cluster, contains 3 data points, 3, 7, 8, 9. On the next iteration, cluster 0 contains 3 data points, cluster 1 contains 4 data points, and cluster 2 contains 3 data points. And the same cluster structure appears after the second iteration. Next, let's visualize evolution of centroids across epochs. Here they can see how centroids for the red cluster, yellow cluster, and blue cluster has been evolved during the K-means clustering training. Finally, let's show how clusters are arranged in two-dimensional space. So this is our clusters, and we can see that indeed access, profile, grant access, and revoke access belong to one cluster. Modify user, delete user, add user, and create user belong to another cluster. And disk array, disk full, and disk space belong to the third cluster. And to summarize, let us also highlight the size of each cluster by drawing a circle around each cluster. For this purpose, we will need a maximum distance in order to use it as a radius for the circle size. So we will compute the distance between the center of each cluster and between each data point in that cluster. Then we find the longest distance and we will use it as a radius. So here we can see the maximum distance for cluster 0, 1, and 2. And finally, let's draw the circles around the clusters. This concludes introduction to K-means clustering with embeddings. In the next videos, I will explain how to measure the quality of clustering, how to decide number of clusters, and how we can next connect together Euclidean distance and a probability, and how we can use the same logic which we use to design K-means clustering code for designing Gaussian mixtures model, which will use probability as a similarity measure. Also, all the code is available in the repository. You can find the link below. You can also check the original support ticket dataset. This concludes introduction to the K-means clustering. Please stay tuned, like and subscribe, and see you soon in the next videos.